Hi everyone, today I'll present to you the operating system that I've been working on, which I'll call it Harx. The word Harx comes from old Japanese word that is harsa, which means excitement. In a way, this operating system is an exciting project for me. So today I'll showcase 4 things about the operating system. Let's start with device independent I/O. We know that there are many different devices in a computer. So those devices have different capabilities, but we want to make them work in somewhat similar way by having device independent I/O. With this, we can initialize them, we can open any stream associated with any device and then use the stream to send a byte or receive a byte. We can also create a resource on those devices if those devices can do that. So there are various devices that our operating system support. Those are capacitive paths, files, LEDs, potentiometer, push button, thermistor, the UART, and then virtual file. Next, let's talk about domain index FAT32 file system. So our file system based on FAT32, but it's a little bit unique that we have domains. Files are living inside domains. There are 3 domains. Those are home, dev, and app. And then in our file system, every files in those domains are indexed. There are 5 different types of index. Those are file, folder, mount point, device file, and programs. Then let's talk about memory briefly. Our memory allocator respects double word boundary and it tries the first possible block that is available. But we also want to reserve the smallest possible block as well. So in a way, it's a combination of first fit and base fit. To make that kind of things work, we may perform 3 different algorithms on any given block. Those are chunking, merging, and stitching, which we will showcase in more detail later on. And then last but not least, we will showcase the multiprocessing capabilities of our operating system. As you know, a process is spawned from a program, and then those processes can block or they can wait for other processes to finish execution. Any given process can also be terminated in our operating system. So yeah, let's talk about next things, which is file system. We'll start with changing directory and then printing the content of directory, creating a file there, writing to a file, and then print the content back. There are actually a lot that I would like to demo, so I may be going faster. So let me start to share the screen and then start the operating system. I hope the font is big enough. Okay, so let's start with ls. We can see the content of a file and then we can go to any directory with cd and we can again change directory. Now let's say I want to create a file. Let me type it me and then let me read the content. It should be empty. And now let's say I want to write something into it, say I'm Adam, and then Control D, and then I can use cut to print the content back. There you go, and we can see that the file now is 9 bytes. The file exists on memory, so we have not mount any disk yet. Now let's do that. So let's say I want to mount an SD card. I say mount and I specify the mount point, let's say my SD, and it's there. And we can go there and ls. It's printing the content of the disk and it's a bit slower, but the next time we do that, it will be much faster because we will have it indexed in the memory. Now I can print the content of a file and say another file and say I want to write into the file and say QQQ and then Control D and I can print the back. I can also create a directory. So let's say I go to DA, to one of the directory, and then I want to create another directory after say A, and there you go. I can also delete or using around the folder. Now we can also create a device file using make node. Let's say I create another thermistor device. I name it TH, and the major ID is 3, the minor ID is 0, and it's there. And we can open a stream for reading for the thermistor device, and there we go. And we can use fgetc to read the thermistor. Yes, we can also use fopen for another device, for any device file. For example, I can read the potentiometer and fgetc from it as well. Right, so that's about the file system. Our memory allocator is a little bit unique because we want to combine both the best of first fit and then best fit. So here is what you will see if you type memory map, and let's say I want to allocate the memory. Malloc, let's say I want to allocate 50,000. This will demonstrate chunking and then print the memory map. So in our operating system, our memory is organized in a way that the leftmost one is once filled and the rightmost one is the one that almost always is free. So here you see that it's created, and yeah, it's chunked into a lot of other free blocks. So the leftmost, so that the first fit can immediately access it if they need space. Then let's say I want to malloc something that is very big. Let's say 888. So there is no free block for this one, but we'll see that the allocator can stitch free blocks together that makes it able for us to reserve that much space. And here you go, we can see that it's reserved successfully. Now let's say we want to free the one at X2B3A9C8, the one at the last, and then memory map. This will demonstrate merging. Those blocks will be merged and it will create a block that is very big. So that's about our memory allocator. The next demo is about Harx multiprocessing capabilities. Process is one of the most complicated subjects about operating system, and it's not possible to explain everything, but anyway, I will demo some. Here you can see that we have an piping operator where the output of ls is processed by the case upper, and we can see here that the text is uppercase, and then we try to spawn touch to LED, and actually it's running already, and we can see that if I put my fingers in capacitive path, the LEDs are turned on, and if I put all my fingers in capacitive paths, then the process is terminated. Actually, almost everything in Harx are processes, so even PS are processed. So you can see that the cell here, when the PS is executed, is blocked. It's waiting for the PS to finish executing until the cell is can run again. Now I would like to demo about the multitasking capabilities, the multitask program. I mean, now I want to create an A text, and then I will multitask on A text. It's actually spawning 3 different processes. The one flashing the LED using PDB timer interrupt. Another one, when I push this push button, will send text on the cell, and then and another one is cat to file, which we are using right now for typing something. And if I push this one, actually the flash to LED program will be terminated. So that's it, it's terminated. And then let's try to control D here after typing something else, something more, and it's terminating the cat to file. And we can see that the A text contains all the text that we have typed. And we can see the PS, it's now has the PS now P13, meaning that there have been many processes that have been spawned before. That's all about process. Thank you for watching all my demo today.